Swayam Prabha. Digital India. Educated India.
How would you solve this? How would you extract meaningful information out of this, I would say, this dump of zeros and ones? How would you do this? But this is what, sorry? Yeah, so yes, that's exactly right. So basically, how do you look for patterns in this? And, sorry? That's exactly what we'll do. That's exactly what we'll do. Yeah, that's exactly what we'll do. Yeah. So at this point of time, as in there's some repeating patterns, right? So these repeating patterns are what your guys are going at. But okay, how do you find these repeating patterns? Another question. But the idea is right. You actually look for repeating patterns. Now let's go back to our, I would say, tool entropy again. But as in not right now, but I would say we'll use this how to tackle this. But let's kind of come back. That's okay. So let us say basically I would say let's cheat a little bit actually. And what happens is if you look at words in English, for example, there is no kernel size for words because the kernel size is varying. But then I think here we'll cheat a bit and say basically as in whenever you're actually encoding all the data on your phones, all the data on your computers, it is not variable length encoding, it's a fixed length encoding. Though variable length encoding is efficient, but I would say language, the reason, for example, let us say you have something, I would say, some friend who has a really long name. Then you'll cut off the later part and just call with the, I would say, first few alphabets or something like that. So why do you do that? Because it's in some sense energy efficient for you to do that, right? You're like, okay, why do you call him again? You call him 100 times a day, but you don't want to call the whole name. So I think so. You try to kind of the most frequent, I would say, the names that you call will be the shortest. That's the reason why a lot of people seem to have pet names or something. They'll have a really long, as in real name, but then at home they'll just call them with 2 syllables or something Chitti or something like that, right? So that's what it is. It's now what you do is basically let's kind of okay, we saw this. So now what happens is, as in all the, I would say, alphabets that you look at, all the digits that you look at are actually, I would say, encoded using ASCII encoding. So as in, have you heard of ASCII encoding before? Yes. So the capital A is denoted by the letter 65 and capital Z is 90 and then small a is 97, this small z is 122. And here is a binary representation for them. And if you take a hello world, with exclamation mark, this is how it translates to. So you're familiar with it. So so what happens is, because in your, I would say, in the memory, I would say the encoding is done, I would say, using 8 bits, or as in new ones basically it's almost, I would say, more bits. But for example, if you look at this, for example, let's say 2 power 8, you have about 256 or so. Yeah. So what you do is basically here, you try to, I would say, kind of say that let's say you assume that basically whatever system that's encoding your data is actually a fixed length encoding system, not a variable length encoding system. And using that, we'll try to do this because basically we are cheating a bit because basically we know the system before. But let's see what happens, what comes out of this. And this is the ASCII table, and I would say you can see, I would say, the alphabets are here, all your alphabets, capitals and small ones, and then all these are control symbols. Basically, as in this is more like, I would say, legacy of telegraph code. And now what we do is basically we'll do, let's say we look at some kind of a kernel size, let's say k. And what you do is you look for this k size patterns all over your data. Why do you do this? The reason is basically you want to see recurring patterns. as in the most trivial thing basically the recurring patterns is kernel size 1. It's 1 and 0. So, but then basically I would say if you look at what, as in, the question to ask is why are we looking at longer kernel sizes? Because basically, because we think that there's higher order information, because basically there's not just 1 and 0s are repeating, so there are only 2 patterns, but then there's higher order information that we want to get at. So, you look at something like I would say some kernel size k, and you're looking at I would say when you actually want to transmit something. Let us say for example, if you actually have, let's say some point in space here. Then the way you would, as in let's say you would represent this as basically something like I hat, some j hat kind of a thing, you do this. But let's say basically if you have something in 3 dimensions and a point here, you do something similar, zk hat. Now for a point in 2 dimensions, you need to send 2 pieces of information. For this one, you send 3 pieces of information. But let's say for example, I tell you basically like okay, there are like I would say let's say 100 points here, and then you send 200 numbers to get the information of all these points. Let's say I have 100, I would say 100 points here, but to send the information I need 300 numbers to be sent. But let's say I tell you one more thing, that let's say this x, this y, this z, and all the 100 points, let's say they lie on a plane like this, if I tell you this. So now, can we do something better? Can it basically, sorry, how, as in, what's the minimum number of numbers you need to send for each one of those points? In total basically you need, so initially you actually needed 200 here, you needed 300 here, but given this piece of information it actually goes down, you can say 200. So why are you saying 200? So what you did was you rotated your axis in such a way that basically instead of using x, y, z, you actually did something like a x prime and a y prime that's perpendicular, which doesn't give any information, and a z. You let the z. You can actually rotate your axis in such a way so that you can make it information efficient or communication efficient in some sense. Is that clear? What's happening here? So what you're looking for is you're looking for underlying structure in the data, and you actually move your coordinate system accordingly to align with the underlying, I would say, structure in the data, and that enables you, I would say, a better code. Is that clear? What's happening here? So what you're doing is basically you're actually, instead of you trying to impose a coordinate system on your data, you ask the data and you align your coordinate system to that particular data set. Okay, that's something that we'll do right now. So what happens is, if I actually have, let's say, code of let's say you have something like 256 is the total number of patterns that you need, patterns that you have. But let us say here basically, if you're actually using only alphabets for your text, let's say capital and small, 26 into plus 26, that's about 52. Let's say using numbers, add another 10, that is about I would say 52, 62, or maybe some punctuation marks, maybe let's under 60 or something. So you don't need I would say so many patterns to represent your data, which if it's textual. Are you with me? So now basically similar to the coordinate system, where you know that the data is on a plane and then you don't need the other coordinate system, can we do something similar here? That is what we are looking at. Are you clear what's happening? We want to eliminate the amount of information that you said. So basically here, instead of sending 8 bits, if there is only basically something like I would say something like let's say 63 or something, 64, then basically let's say for example you have something like I would say 64. 64 is basically what? 8 into 8, that's about 2 power 6. So what you need is basically you can do away with 6-bit encoding. Do you see what's happening? So to actually represent 64 of these patterns, if I need 64, then 6-bit encoding is sufficient. Are you with me? Are you lost? Sorry? Sorry? 0. Sorry, 0? 0 to 63, yeah. But the total number of patterns you need is 64. That means basically you can do away with 2 power 6. That's basically, that's a 6-bit encoding. You don't need an 8-bit encoding for it. That's what it is. So now let us see what happens. So I'll show you a plot and explain to you what's happening here. This way. So what happens here is, so let's say we took the kernel size, and you take a varying kernel size length and you move it across, and you look at the number of patterns that you see. Let us say if you have, I would say, let's say something of 1-bit length, then you actually have 2, the maximum possible patterns that you see. If you have, let's say it's of length 2, and the maximum possible patterns is 4, and so on, you can enumerate. And so basically that's the maximum number of patterns. But then what happens is, whenever basically your text has all the patterns, maximum number of patterns, there's no way to compress it, because you're using all the patterns. But let's say basically if your whatever patterns that you're seeing, let's say the total number of possible patterns is, I would say, much greater than the number of patterns that you see. The gap is high, then you have a chance to compress. Are you with me? You see what's happening? And that is what we'll try to exploit here. So what you see here is basically, let us say almost like here basically, let's look at the blue line, this one. So what you see is basically the total number of, I would say, patterns that you're seeing in the text, I would say, is increasing gradually, but it reaches 7. But the total number of patterns when you hit 8 is actually decreasing, which would actually increase, right? The total number of possible patterns when you have 7, that's 2 power 7, that's about, I would say, I think 128 or so. So basically you have, this is the total number of patterns in 7, but when you do 8, basically what happens is the total number of patterns that you should is 256, but if you are using alphabets basically, and I would say numbers, actually let us say basically we are only using something like 64 or something, let's say, something like that. So what happens is, we are actually not using a bulk of them. You're seeing that, and that is what is this dip here. And now you are actually quantifying that, and you're saying basically, I would say, let us say I define something like how much is the difference. So what I do is, I take the total number of patterns that are in my text, but the total number of patterns that are actually theoretically possible, let's say the total in capital T. And then basically, as in, this will actually go down if it is, I would say, if it's information efficient, communication efficient, the number of patterns is less. Then what you do is basically you want to make it an increasing function, you will do this. And this basically you can call the compactness score. How compact your code is. Are you with me? Are you lost? So that means, sorry. So what I'm saying is, you have, I would say, for some kind of encoding scheme, there are a lot of patterns that are possible. Just akin to 3 dimensions, you have a lot of points. Points can be all over the place. The very as in point that all these points lie on a plane implies that I can actually rotate my coordinate system in such a way, like I can define x prime and y prime, where y prime doesn't give any information, x prime, and then I actually can do it with 2 dimensions, right? So now what I'm trying to say is, let us say basically you have 256 possible patterns. But out of it, you're using only 63 or 64 patterns. Then you don't need a 8-bit encoding scheme. You can do a with 6-bit encoding scheme. Are you with me? So what we are looking at is, a priori you don't know that. So what you'll do is, in this text, you look at patterns of length 1. The maximum possible patterns of length 1 is 2. Agree? Yeah. Similarly, basically the total number of patterns in this particular text is already 2, because if you look at basically, I would say, of length 1 and 0 stop. Now you take patterns of length 2, and you will see 0 0 will be there, 0 1 is there, 1 0 is there, 1 1 is also there. So that also doesn't give any information, because basically almost all the patterns are there. You keep doing for 2, 3, 4, so on up to different encoding lengths. And then at a specific encoding length, what you see is the total number of patterns is very high, possible. But the patterns that you see is just a fraction of it. And that is what the curve is showing actually. Yeah, here. So basically, if you actually look at total number of patterns that you're seeing, it actually dips. And when you actually try to look at this kind of a thing, it's not just the total number of patterns, but relative to the total possible patterns, then actually you see a spike here. Are you with me? So that means basically you are able to extract the encoding, what is the encoding length? Are you with me? In this case you will take 8. As in, don't worry about other dips here, because I would say, because 12 is, for example, let me ask you a question. Why is there a dip at 12? Why is there a dip at 12? There's a dip at 8, I can understand as the encoding length. Why is there a dip at 12? Think about it. We will come back to this at the end. Ask me then. But I would say, but there's a dip at 12. What explains this? But anyway, I think for now, let's take 8 and move on. Okay? Okay, you understood this? Okay, if you understand this, I have a question for you. Now, let us say basically I would say all the characters, basically all the alphabets and numbers. That's only 64 patterns, right? Now, what I do is, I'll add some noise to this. Let's say you have some CD or something, it gets scratched. So, some zeros become 1, some 1s become 0. Now, out of the 64 patterns, you flip these bits and suddenly basically let's say you have all 256 patterns. Are you getting what's happening? What's happening is, initially you only have, I would say, patterns, 64 patterns or so, because you are using only alphabets and digits. Now we actually kind of try to see that basically that, okay, I look at this kind of a score. These are the total number of patterns that I'm seeing in my data, but these are total possible patterns, and that gap I'm exploiting to get my encoding length or something. Now what I'm saying is, I'm going to flip some of these bits in the 64 bit thing. I say out of 64 patterns, I flip some of these bits, and now all of a sudden I have all the 256 patterns. You're getting the point, what's happening? Are you with me? Now you have all 256 patterns and this will fail. Do you see? Because on the top, if you look at the total number of patterns, that will be 256. Theoretically possible patterns is also 256. That will become a 1 and this will become 0. Now the question is, how do you solve this? How do you solve this? Basically, earlier we wanted to kind of see, let's say we did a kernel size and we kind of ran across this. We saw the number of patterns. The total possible patterns is much higher. We saw there's a gap and we want to exploit this gap. Now the gap is no more there. Now what will happen? How will you overcome this? Errors came, everything got flipped. Now all 256 patterns are there. Okay, so let's kind of, I would say, let's go to the next step. How would we do this? Is basically, let us say, for example, you have this 64 patterns, right? So let us say basically the errors, it's not like errors occur all over the place. Errors, there's some scratches. So basically, let us say basically you have about 5% bits of flip, let's say, or 2% bits of flip. Now what happens is basically when you're flipping, let us say you have something like one, let's say, I don't know, let's say not. Let's take, let's say A or something here. 0, 1, 0, 0, 3 zeros, 4, 5, 6. Okay. This is how it looks like, let's say. Now, So let us say your A, let's say in the novel there is an alphabet called some alphabet A. Now, this is how it's represented in your computer memory, because that's how 65 corresponds to this. Now, let's say some scratch happens, some error kind of comes in, and let's say this bit flips to 1. Now, this is no more a capital A, it will be something else. So, this is what happens, I'm saying. Okay, are you with me? Sorry? So, let's look at basically what this thing is coded for. Basically, I would say, what happens is, let's say if you actually have 1 here, that will be greater than 128. So basically this one, basically when you have 1 here, that is, let's say, for example, this is like 2 power 0, and this is 2 power 8, and this is 2 power 7. So let's say, for example, if you actually want, 2 power 7, 2 power 6. Okay. So what happens is this is 128, this is 64, and this is a 1. This is 12, 13, this is a 9, 193. 193 is it? So what's at 193? Okay, this table doesn't have 193. There's probably some other symbol that will show up. That's why you'll get you'll not get an alphabet. Probably basically you'll not get English alphabet. Maybe let's say if there's some Spanish alphabet sitting there, you'll get a Spanish alphabet. Let's say you have something, I don't know, maybe something like a let's say German alphabet like umlaut or something. You get something like that. So that's when basically your text get corrupted. Sometimes basically you see random symbols, right? So basically the encoding went haywire somewhere. Okay. So now let's come back to our thing. What we said was I have my data, and now what happened was basically everything was clean. Then I looked at kernel, I looked at the patterns of different size, I ran it across, and then I saw the gap between theoretical possibility and what I'm seeing in my data, and I'm exploiting that. And now because of bit flips, all of that went haywire because basically my formula will no longer work. And what you'll get is something like, I would say, okay, forget about this. Basically, I will come back to this. But here, what happens is earlier you saw something at 8 here. 8, there was a dip in the compactness score, or there's a spike in the compactness score. Now there's no spike. Number of unique patterns, there used to be a dip here. Now there's no dip. Everything is gone. So now what you look at is one observation to make here is, let's say if all of your alphabets, basically you're using only alphabet stuff, basically what happens is almost all the numbers will lie less than 128 because all the alphabets are, I would say, encoded with less than 128. That's one thing. So you can actually say, okay, if there's a bit flip here, that's wrong because basically if there's bit flip here, it goes beyond 128 and that's not right. But I would say, for example, let's take more, I would say, a different argument here. Let us say, for example, if a bit flips on this thing. So the probability of a capital A kind of becoming this is, let's say, I would say, let's say 2% or something of all the things, of all the patterns. That means you actually have the number of times, basically the number of, I would say, counts on A, B, C and so on and so forth. The number of patterns, you're getting the point. So what happens is when a bit gets flipped, the number of times this pattern shows up is much less. Are you with me? Now you look at all the patterns and not just the patterns but also look at their counts. And now you look at basically you can kind of put a distribution on this and kind of, let's say, for example, you're randomly picking a pattern. What is the probability of it being a specific pattern? Are you with me? What is happening here? You have all the 256 patterns, but of all the 256 patterns, you initially basically you just looked at the pattern appearing or not, but you're also looking at the number of times it's appearing, because basically if it's an error, it's due to some noise or some error or something, the number of times it will appear is much less, assuming that the noise is low. So that is what you want to exploit now. That is a key observation that you want to make. Now once you have made this, then how will you kind of discover basically your, I would say, your patterns again? What is the correct encoding length and things like that? Now what you do is basically you actually, instead of looking at, I would say, initially we're just looking at counts. Now you take that counts and replace it by the entropy of the counts. So what you get is something like this. So here is the what you have is basically it's the total number of patterns here. And what happens is if all the patterns were equiprobable, then the entropy is highest. Because basically some patterns occur with high frequency and some patterns occur with very low frequency, there's structure underlying this data and you want to exploit that structure. And when you do that, as in basically, let's say if you have more certainty on certain patterns and less certainty on some other patterns, then the entropy will go down. So your numerator will be much less than the denominator. And that is what, for example, we visited that, we did the entropy thing. No? So basically, if there's uncertainty, more uncertainty, the entropy is higher. Less uncertainty, it's a bit lower. So what you try to do is basically, when it's totally random, what happens, there's no structure in the data, your entropy is maximum. But then when you actually, for example, if there's some structure in the data, but due to some errors, some other flip, but still there's a lot of structure in the data, so that shows up in the entropy. And now what you're seeing in this plot, so let's look at this one. So what you see is basically you actually see that I think this is the old score. Basically it's flat, basically there's no spike here, but if you actually look at this score, this actually peaks here. So now what this means is you know that there's something happening at 8, the encoding length is 8, that's what it is. So now what you do is basically, okay, now let's say for example we have, I would say 8 as our encoding length, so we inferred the encoding length, and now once we inferred the encoding length, you look at all the patterns that this is producing, and then you actually look at basically how frequently they are occurring, and this is how they will show. As in, at below basically all these are the patterns, and these are the ASCII letters that they correspond to. So what you see is basically most of the, I would say, the English letters basically, I would say, are coming up with very high probability, but whereas basically I would say later on, if you actually plot more of this, basically there will be some gibberish also that came from, I would say, some errors and bit flips. So what you just did was basically, without, I would say, let's say, any information about the structure of the underlying data, you are able to extract some information out of it, and what you extracted was the patterns that are governing English alphabets here. So any questions? Are you lost? Are you with me? Yeah, please.
So if we do the kernel scan, we go like for K, we go from the first to the 7th, and then from the second to the 8th.
No. So basically, as in, the assumption here is, let's say for example, if your data is encoded, right? Let us say if alphabet A is encoded with 8 bits, right? Then what that means?
When we scan to
Yeah. So what you do is, you do K here like this, and then you start from here and do a K. The reason is because if you start here, then the structure is lost. Getting the point? So you are always assuming that you are starting on the right bit. If you are not starting on the right bit, everything will get screwed. But that also you can handle. But so I am skipping all those details that can be handled. But assume you are on the correct bit in the first one. Then you jump 8 bits, you get one alphabet. You jump 8 bits, you get another alphabet. So on and so forth. Yeah, please.
Get more entropy or lesser entropy?
Sorry.
Do you want a great higher entropy or
So if you want, I would say when you're actually getting information, more information, I would say the uncertainty decreases, the entropy goes down. So what happens is, let's look at a small case. Let's say for example, let's say you look at something like coin toss. Let's say the probability of getting a heads is, let's say, P, getting tails is 1 minus P. So now what's the entropy for this? Let's write it down. Okay. Now if you ask when is this maximum, this will occur when P is equal to half. That means if you actually look at probabilities, if you do this. So what this means is basically H half log half plus another half log half. So all of this, obviously there's a negative sign here at the end. So this is 2 minus 2 log half. This is 2. But then if you put something else here, let's say you put 1/3 on this and 2/3 on this. This for H, let's say this is called H naught and H. This H will always be less than H naught. The reason is here there is more uncertainty because here it's half, but here there's less uncertainty in some sense because basically it moved in favor of tails. Getting the idea? So what happens is basically you want more certainty. If you want more certainty and you actually want to push the entropy down. So this is what's happening here. The ideal thing is you want to push it down to 0. But even if that's not happening, at least if you know the band around where it is, if you actually minimize it, that's okay. So our idea is to push the entropy down so that basically we can extract the information.
does the drop in the peak when we have 12
Sorry?
There's a drop in the peak.
Ah.
How would we attain 8? Does the drop in the peak in the graph show?
So basically, so let's go back to this graph. That's right. So, okay. So what's happening here is basically what I'm actually following here is basically I'm actually not just looking at this line, the number of unique patterns, but what I'm actually looking at is I'm looking at the red curve, which is actually something called a compactness score. That is actually relative to the total number of possible patterns. If 8, basically it's about 2 power 8 patterns, but for 12 it's 2 power 12 patterns in the denominator. So that will push it down. Yeah, please go. I'm sorry. Yeah, so what happens is right now from here, it's very difficult to make out what to take from here. I'll tell you, for example, as in this is going up and up, so basically compactness gain is very high here or something, that can be the argument. So what we'll do is basically instead of looking at it, I'll tell you why it's actually, I would say, plateauing on the top. But I would say, if you actually look at here, what happens is if you want to pick this point, it is not very clear what point to pick. But if you actually do a delta between, let's say, the point and its neighborhood, let's say basically, let's say you have compactness gain, compactness score at 8 and compactness score 7. You do a delta between them, you kind of take the difference between them, and now it shows up very clearly here.